Good day, ladies and gentlemen. Phase diagrams normally consist of phases, and these have an impact on the material properties. These are some of the definitions or terms that you'll come across. A component is a chemically recognized species. This could be your zinc, your metals, or even your carbons. Then we have a phase. A phase is a portion of a system that has uniform physical and chemical properties and is separated by a boundary from other phases. Then homogeneous phase is just one continuous phase. And a solvent is the major component in a solution. And while solubility limit is the maximum that a solvent can take of a salt. We have already said the properties of a material depend on the phases that will be present in our material. But beyond that, not only are the phases, the composition of the phases, but also the structural arrangement of these phases will affect the properties of our materials. An example here is given where we have a long gray region, flakes of graphene, and the other phases that are there, we have the ion phase, the body-centered cubic phase, and we have also the iron carbide phase. Under the binary phase diagrams, we have the isomorphous diagram. In this case, two components are completely soluble in the solid phase. For a given temperature and composition, we can determine the concentration of each phase, the composition of each phase, and also the relative mass fraction of each phase. Summary of the diagram, we have the regions. We have the top region where we have the liquid phase, and then we have the region between the red lines. The top part is the boundary is called the liquidious line, while the bottom part is the solidus line, and in between we have a mixture of both solids and liquids. Then we have the bottom part where we have our solids. This is how we determine the composition of our material. So in this case, we are looking in the region where we have both the liquid and the solid, and you want to know what's the composition of our liquid phase and the solid phase. So this is done by drawing a tie line through our point, and this point is defined by temperature and also composition. So in this case, it's XB and a certain temperature. And then we draw a tie line that touches the liquidious line and the solidus line. And the composition of the liquid in this part will be XB liquid, or at least the composition of the solid will be XB, where the tie line touches the blue line or the solidus line. So the other thing that you want to do is to determine the amount of phases that are present in our mixture. So we have our green point, which is determined by composition and also the temperature in the phase diagram. Then we draw a tie line, and this tie line touches the solidus line and also the liquidious line. And to determine the portion of for example, the liquid part, or in this case the upper part, we take the length of that and divide it by the overall length of our tie, and the derivations are done here. And at the end of the day, for this example, you will see that the weight fraction for the liquid will be concentration of Cp minus the initial concentration, which is where our lever is pivoted, divided by concentration of our beta minus concentration of our liquidius or liquid, which represents the whole length of our tie, and this will give us the fraction, which is liquid. And then we also have the case we want the fraction for the alpha part, which will be C naught minus CL divided by C beta minus CL. An example of how to calculate mass fraction is given here below, and we have already said, so for us to calculate the mass fraction of the liquid part, is WL will be equal to the length of S divided by the whole length of our tie line, which will be S divided by R plus S, and representing this in terms of concentrations. So S is represented by C alpha minus C naught, and the whole length is represented by C alpha minus CL. Then we get the fraction that is liquid. Then for the fraction which is solid or alpha, this will be R divided by the whole length of the tie, which is R plus S, where R will be represented by C naught minus CL divided by the whole length, which is C alpha minus CL. This is how the microstructure develops for an isomorphous alloy in a case where the cooling is very slow. So we'll take this case where the composition is 35 weight% nickel and the temperature is at 1300 degrees Celsius. At that point, our material is liquid, and it is composed of 75% nickel and 65% copper. And if you slowly cool this to point B, and this point B is at our liquid gas line, and it means we are now starting to have both phases, the liquid and the solid. So in this case, the composition of the liquid will be still 35 weight% nickel, whilst the composition of the solid will be 46% nickel. And this is observed through the use of the tie line. And as you cool further to point C, and you now have this new composition, our solid phase will have a composition of 43 nickel, and the liquid phase will have a composition of 32 nickel. And if you continue cooling until we get to the solid gas line, now we have our solid having a composition of 35 nickel, and the liquid phase will have a composition of 24% nickel. And if you cool further now into the alpha phase, we now have our solid having a composition of 35% nickel. And the diagrams illustrate how these solids are formed. In a case where the cooling is so fast that equilibrium is not reached, you will take the same point and do an analysis. So in this case, you realize that the composition that is taken is 35% nickel and temperature 1300 degrees Celsius. As you cool down and you get to the liquid gas line, we have the liquid which has a composition of 35 nickel and the solid which has 46% nickel. And as you cool further to point C, you will now have liquid which still has the same composition as the slow cooling, because diffusion is fast in liquids. Whilst for the solid, ideally the solid that should be formed should have 40% nickel, but in this case what you have is the new composition is around 42%, and this is because the earlier solid which was formed, which has a higher concentration, has no time to dissolve and be in equilibrium with the new solution concentration. Therefore, you produce a material that is made of many layers. So the first layer of our material was 46%, the second layer is at 40%. Then the new average, or the new, if you integrate that in some of those differential layers or different composition in different layers, you get a composition of 42%. nickel. And if you move from C to D, similar thing happens. And if you continue moving, you realize that there's a slight shift in the compositions to the right. So with the challenges of materials made of different layers is that as you do heat treatment or as you work on them, there is bound to be premature failure because of these different grains, boundaries, because of these different phases or different composition produced during the fast cooling. Another system that you have is a binary eutectic system. In this system, we have a liquid form phase that transforms into two different solid phases upon cooling. The solubility limit corresponds to the maximum concentration of one component that will go into a solution in a specific phase. The solubility limits in this case are the solidus and the solvius phase boundaries. Here is an example of a binary system, of eutectic binary system. In this case, the phase diagram has copper and silver. In this diagram, we have three single phase regions, which are your alpha, your beta, and the liquid phase. We have three two-phase regions, which is your alpha plus liquid, your beta plus liquid, and your alpha plus alpha. Liquid and solids exist in equilibrium in a point called eutec composition, which is Ce, and at a eutec temperature. We look at how the microstructure of a eutectic alloy or system is developed. On the diagram on the left, we have a system which has high composition of lead and low concentration of tin. At a point labeled A, we have the composition of the liquid being C1 weight percent of tin. If this is cooled to point B, we will have two phases being produced, the liquid phase and the alpha phase. And if this is further cooled to point C, we have a alpha phase solid being produced, which has a composition of C1 weight percent tin. For point B, we should be able to get the compositions of alpha and L using the tie line. On the diagram on the right, we'll look at the system starting at a point D, where the composition of the liquid is C2 tin, and if this is called to C to E, then the composition will now the phase will consist of alpha and the liquid phase, and the composition can also be determined using the tie line. And then if you move further to point F, in this point we have the composition C2 of our tin for the alpha phase, and at the bottom at point G we now have our solid phase alpha and beta having a composition of C2. And now we look at a case where the composition is now C3 and we're starting at point H. At this point we have the composition of the liquid being 1.9 weight percent tin, and as you cool down you reach the eutectic point, and if you cool further you get your alpha and beta solid. Eutectic reactions involve redistribution of the metals, in this case your lead and your tin. This leads to a layered structure as shown in the figure. So in the previous case, we looked at a case where we have one liquid phase forming these two phases, the alpha and the beta phase, and we say this produces a layered microstructure. But in this case, we are moving from alpha liquid phase. So in this case, we already had solids, which were alpha. And in this case, they had 18% tin. And if we move to the region where we now have our alpha and beta solids, what we have is a structure that builds around our primal alpha solids, and a eutectic structure is formed or built around those primary units. Another system that we have is eutectoid system. In this system, we have one solid phase producing two new solid phases. As shown at point A, we have the sigma phase that produces gamma and epsilon phase. Another system that we have is peritectic system of reactions. In this case, a solid and a liquid phase produces another second solid phase at a particular temperature and composition, as shown in the diagram on your right. Another phase transformation that you have is congruent phase transformation. This is a transformation where the change in phases leads to no change in composition, as shown in the diagram on the right. And a typical example is transformation of alpha ion to gamma ion. One of the most used materials is steel, and steel is an alloy of iron and carbon. A phase diagram for iron copper is shown on the following page. This is a phase diagram for steel. We have the alpha ferrite, which is a solid solution of carbon in body-centered iron. It is the stable form of iron at room temperature, and there's a maximum solubility of 0.02% of carbon, and it transforms to face-centered cubic gamma austenite at 912 degrees Celsius. Gamma austenite is a solid solution of carbon in face-centered iron. Maximum solubility of carbon is 2.14%, and it transforms to body-centered delta ferrite at 1395 degrees Celsius. It is not stable below the eutectoid temperature of 727 degrees Celsius unless cooled rapidly. Delta ferrite solid solution is a solid solution of carbon in body-centered iron. The same structure as the alpha ferrite. It's only stable at temperatures above 1394 degrees Celsius, and it melts at 1538 degrees Celsius. Cuprite is one of the stable forms of iron. And this is just a short summary of this phase diagram. This brings us to our phase diagrams. But mostly important, you still need to look at the development of microstructures for steel. And this as an emphasis, these are guidelines for what you should read on our reference textbooks. This is not enough for you to pass in the exam. This is the common classification of our ferrous alloys. We have iron, and this is typically a material that consists of less than 0.08% carbon. And we have steels, which consists between 0.08 to 2.14% carbon. And those are the examples. And the last class that you have is cast iron, which consists between 2.14 to 6.78% carbon. And have an understanding where these are most practical or where these are most desirable. This brings us to the end of our lecture on phase diagrams.